Hello, a very good day to everyone. So for today's video, under the topic under computer graphics and visualization, the topic is as follows. So let us see the topics for today. So for today, my topics are the 2D viewing pipeline, 3D viewing pipeline, and the color models, that is the RGB color model and CMY color model. So first, what is 2D pipeline viewing? Let us see. A section of two-dimensional scene that is selected for display is called a clipping window. Sometimes the clipping window is alluded to as the world window or viewing window. Graphic packages allows us to also control the placement within the display window using another window called viewport. So viewport is nothing but another window through which the graphic packages can be viewed, and the controlling of that particular image can be seen. The clipping window selects what we want to see. The viewport indicates where it is to be viewed as the output device. So clipping window selects what we want to see, and the viewport indicates what is to be viewed. So these are the two actions performed by the clipping window and the viewport. By changing the position of a viewport, we can view objects at different positions on the display area of an output device. Usually, clipping windows and viewports are rectangles in standard position with rectangle edges parallel to the coordinate axis. So 2D viewing pipeline is nothing but the two-dimensional viewing of the pipeline, where the two-dimensional scene that is selected for display is called the clipping window, and the viewport is nothing but through which the graphic packages allows us to control the placement within the display window. So next, we first consider any rectangular viewports and clipping windows as illustrated. So the mapping of two-dimensional world coordinate scene description to device coordinate is called a two-dimensional viewing transformation. This transformation is simply referred to as the window to viewport transformation or the windowing transformation. So the transformation of two-dimensional viewing with reference to the device coordinate is referred to as the window to viewport or window viewing transformation. We can describe the steps for two-dimensional viewing as indicates in the figure. Once a world coordinate scene has been constructed, we could set up a separate two-dimensional viewing coordinate reference frame for specifying the particular reference frame for specifying the clipping window. So as we can see in this diagram, there are the world coordinates and the viewports. Okay, from the world coordinates, we can see this diagram is like a big mountain where it consists of, it is not clipped, that is the clipping window. Whatever the rectangle is there, it is the clipping window. Once the clipping window is done, then the image can be viewed as the follow in the viewport coordinates. So clipping window can be used to take out the unwanted lines or unwanted objects and only clip the particular image which we want to focus on. So viewing a pipeline. Okay, the mapping of two-dimensional world coordinate scene description to device coordinate is called a two-dimensional viewing transformation. This transformation is simply referred to as the window to viewport transformation or the windowing transformation. We can describe the steps for two-dimensional viewing as indicated in the figure below. Once a world coordinate scene has been constructed, we could set up a separate two-dimensional viewing coordinate reference frame for specifying the clipping window. To make the viewing process independent on the clipping window, to make it independent, the requirements of an output device, graphic systems convert object description to normalized coordinates and apply the clipping routines. Systems use normalized coordinates in the range 0 to 1, and others use normalized range from -1 to 1. Systems use 0 to 1, and whereas the others normalized range is -1 to 1. At the final step of viewing transformation, the contents of the viewport are transferred to positions within the display window. Clipping is usually performing normalized coordinates, that is, the normalized range of systems is 0 to 1. So in that place, the clipping is normally performed. This allows us to reduce computations by the first concatenating the various transformation matrices. Concatenating is nothing but adding or merging of the two matrices, whatever we have obtained from the coordinates. So let us see the diagram over here. The MC, that is the modeling coordinate transformation. Construct world coordinate scene using modeling coordinate transformation. With the help of MC, we construct world coordinate scene. With the help of world coordinate, we convert convert world coordinates to the viewing coordinates, and with the help of viewing coordinates, we transform normalized coordinates. Normalized coordinates, we transform it into map normalized coordinates to device coordinates. So transforming viewing coordinates to normalized coordinates, map normalized coordinates to device coordinates. So this is the simple explanation about the 2D pipeline, how it is constructed and how the modeling is converted to viewing. Then from viewing it is converted to window, and from window it is converted to normalized coordinates. So the next topic is the 3D viewing pipeline. The steps for computer generation of a view of 3D scene are analogous to the process of taking photography by a camera. For snapshot, we need to position the camera at a particular point in space and then need to decide camera orientation. Finally, when we snap the shutter, that is the shutter in the camera, the scene is cropped to the size of the window of the camera, and the light from the visible surface is projected into the camera film. So 3D view pipeline is that we have taken example where whenever we click a pic in a phone, it comes only up to a clipped part of the camera. So to the size of the window, camera light from visible surfaces projected onto the camera film. So we can see a modeling coordinate, modeling transformation, modeling coordinates, then viewing transformation, viewing coordinates, projection transformation, projection coordinates, workstation transformation, device coordinates. This is how the process is taken place in the 3D pipeline. So let us see what are the projections and nothing but once world coordinate description of the object in a scene are converted to viewing coordinates, we can project the three-dimensional objects onto the two-dimensional viewplane. There are two basic projection methods. They are the parallel projection. In parallel projection, coordinates positions are transformed to the view plane along the parallel lines. So it is basically same as the 2D pipeline. By using the 2D pipeline only, we are also like constructing or seeing the process of the 3D viewing pipeline. So next topic is the color models. Okay, whenever color models, first we need to see what are the color models. Any method for explaining the properties or behavior of color within some particular context is called as color model. So there are basically two types of color models. First one is the primary color models and the second one is the intuitive color concepts. The hues that we choose for the sources are called the primary colors, and the color gamut for the model is the set of all colors that we can produce from the primary colors. Two primaries that produce white are referred to as complementary colors. Examples of complementary pairs are red, cyan, green and magenta, and blue and yellow. Intuitive colors are the color concepts. An artist creates a color painting by mixing color pigments with white and black pigments to form various shades, tints, and tones in the scene. Starting with the pigment for pure color, the artist adds a black pigment to produce different shades of that color. Okay, whenever we take a particular color, for example, red, when we add black to it, we can produce the from darkest shade to the lightest shade by using white and black. In the same way, that is called as the intuitive color concept. Primary colors are mixing the two primary produce white, so that is called as primary colors. So intuitive is we produce more shades, so that is the only difference between the primary colors and the intuitive color concepts. Tones of the colors are produced by adding both black and white pigments. So let us see what is the RGB and CMY color models. Okay, RGB color model. According to the Tristimulus theory of vision, our eyes perceive color through the simulation of three visual pigments in the cones of the retina. One of the pigment is most sensitive to light with wavelength about 630 nanometer, that is the red. Another has its peak sensitive at about 530 nanometer, that is green, and the third pigment is most receptive to light with wavelength of about 450 nanometer blue. The three primary red, green, and blue, which is referred to as RGB color model, can be represented in the given cube. The origin represents the black and diagonally opposite vertex coordinates 1, 1, 1 is the white, and the RGB color scheme is an additive model. Each color point within the unit can be represented as a weighted vector. Some of the primary colors using unit vectors are G and B. C of lambda RGB RR plus GG plus B, where red, green, and blue are assigned values in the ranges from 0 to 1.0. From in the given cube, we can see the coordinates and the color systems. That is, all the zero zeros represent the black color and all ones represent the white. Blue is 001 and red is 100. When we mix this, we get the another color model, that is CMY color model. Let us see in the next slide what is the CMY. CMY or CMYK color model. A subtractive color model can be formed with the three primary colors, cyan, magenta, and yellow. The unit cube representation for CMY model is illustrated in the figure. Here you can see the red, magenta, blue, black, all have been displayed within the coordinates, and when they mix together, they form the different colors. Let us see in the next slide how the colors have been formed. So first we have to see what is the CNY. In the CMY model, the spatial positions 1, 1, 1 represents black because all components of the incident light are subtracted. The origin represents white light. Equal amounts of each of the primary colors produce shades of gray. Along with main diagonal of the cube, a combination of cyan magenta ink produces blue light because the red and green components of the incident light are absorbed. Similarly, a combination of cyan and yellow ink produces green light, and a combination of magenta and yellow ink yields red light. So the main keyword that we have to keep in mind is the which two colors gives the following color models. So the printing process often uses a collection of 4 ink dots which are arranged in a close pattern. So somewhat as an RGB monitor uses 3 phosphor dots. Thus in practice, the color CMY color model is referred to as the CMYK model, where K is the black color parameter. 1 ink dot is used for each of the primary colors and 1 ink dot is black. So in this slide we can see here the red RGB, that is red, blue, green, that is the basic primary color model. Okay, whenever green and blue is mixed, we get cyan, and when red, blue, and green all are mixed, we get the black color, and yellow and we get the yellow magenta. When green and red are mixed, we get yellow. When blue and red are mixed, we get magenta. So this is for today's video. We have seen about the 2D viewing pipeline, 3D viewing pipeline, and also the color models. Those are the CMY color model and RGB color model. So thank you. Have a nice day.